Okay, now that we've talked about some of the basics for significance tests in general, let's get very specific. First, we're going to get specific about categorical data, which means proportions. Okay, we're back to P and P hat. We're going to do just like we did with the confidence intervals. And the first thing we're going to do is talk about P and P hat. And then the next thing we're going to do is talk about mu and X bar. Okay, so the first one is categorical data. And the first thing we need to talk about are the conditions. If we're actually going to do a significance test for a population proportion, what are the conditions? The first one is random. As always, it must be a random sample, or if it's an experiment, random assignment. And number two is normal. Okay, if we're talking about normal, that's the NP one. Okay, because this is categorical data. So it's not like it actually could come from a normal population. So this is where you have to say sample size times the proportion greater than or equal to 10. Sample size times 1 minus the proportion must also be greater than or equal to 10. And the question is, what proportion am I using here? You are going to use the null. So I'm going to put P sub 0 here because this is the null value. Because remember, we always assume that the null is true. We always assume the null is true. So when we're calculating our conditions, we are going to use the null. 3, independent. Okay, either your results are independent of one another or more than likely, this is going to be the 10% condition. If it's sampling, it's the 10% condition, which remember is that 10 times our sample size must be less than or equal to our population. So that our sample size is 10% or less of our population. Okay, hopefully you have noticed that these are the same 3 conditions that we use for a confidence interval. The only real difference is that when you are calculating this, you're not going to use your sample proportion, your sample p hat. Okay, don't use p hat. You are going to use the null value because that's what we are assuming to be the actual truth. Okay, then something that's a little different with significance tests is that you have a test statistic. Okay, this does not mean anything different than a z-score. Basically, it measures how far the sample statistic is away from the mean in terms of standard deviations. So out of my sampling distribution and all the p hats I have, okay, if my sampling distribution, remember, is if it's of p, then all of these values are p hats. And the one right in the middle is my true value of p. And so if this is the one that I have, how far away in terms of standard deviations is that? Hopefully that reminds you of something that you've been using most of the year, a z-score. It's going to be the same thing. It's your p hat value minus the null divided by the standard deviation of p hat. And the reason that we're using the null here is because we assume that it's true. So we assume it really is p. And remember, this right here is the square root of p times 1 minus p over n. And you can probably guess by now that in these values, you are not using your p hat value, you are using the null. Okay. Test statistic. This is not on the formula sheet per se. It's written in words. It says like test statistic equals statistic minus parameter value divided by standard deviation of the statistic. Your null value is your parameter and your thing that came from the sample is your statistic. Okay? We're calling it test statistic now. It's really it's the same thing as z-score. So let's revisit. I don't know that we ever actually talked about Jack's campaign for mayor, but let's talk about it. Jack needs 50% of the votes in order to win the election, and in an SRS of 100 votes, 56 favored Jack, which right there, that tells us that our P hat is 0.56. So let's check the conditions. Okay. 1, random. Okay, it's an SRS. So that right there said that it is random. 2, the normal condition. 100 is our n value times 0.5 because we use our null. Because in this case, h sub 0, our null, would be that the proportion is equal to 0.5. Because if there is no difference, then half of the people like him. Okay? The alternative would need to be P is greater than 0.5 because we want him to win, and he needs more than half the votes to win. Okay, so 50 times 0.5, or 100 times 0.5, I'm getting a little ahead of myself, would be 50. And likewise, to do 1 minus P would be the same thing. And 3 would be independence, where we can assume more than 1,000 people voted. Okay, calculate the test statistic. We'll do that over here, kind of out of the way. The test statistic is going to be our parameter, and because I'm working with proportions, it's Z. Okay, our parameter, our statistic, our P hat, 0.56 minus the parameter divided by the standard deviation, which would be 0.5 times 0.5 divided by 100. And when I work all this out on the calculator, I should get 1.2. Okay. Obviously, our sampling distribution here is normal because both of these checked out. So to find, did I interpret my p-value, I just go back to my good old trusty table A, and I want greater than 1. Okay, or my good old trusty calculator, and I'm going to get a p-value of about 0.1151, which means that if exactly 50%, so if my null is true, if exactly 50% voted for Jack, there is about a 11.5% chance that 56% would vote for him in a random sample of 100. And I'm running out of space. Okay, would vote for him in a random sample of 100. So that's what the p-value means. Okay, we talked about that some yesterday. If exactly 50% voted for Jack, there is about an 11.5% chance that 56% or more would vote for him out of a simple random sample of 100. Okay, so let's talk specifically about the 4 steps. You know what the 4 steps are. We've done them all year long. They have not changed. They will not change. State, plan, do, conclude. What do you need to do in each of these steps? Okay, in state, you need to do your hypotheses, determine your alpha level, and define your parameter. In plan, choose your method. As you can see from the header on this page, the one we're talking about today is your one sample z-test for a proportion. But you might be using a confidence interval for a proportion, or a confidence interval for a mean. Okay, so choose your method, check your conditions. Okay, in the do, calculate the test statistic, and find your p-value. And then conclude is kind of self-explanatory. Always interpret them in context. That's the big thing that people forget. Make sure you always do this in context. Okay, talked about this a little bit. We use Z here. And no, it's not on the formula sheet, but it's on the formula sheet in words. And what happens when your data doesn't support your alternative? So let's say, like in this one, my null was P is equal to 0.5. My alternative was P is greater than 0.5. But what if I get data, and in my data, my P hat was actually 0.3? Okay, this does not support my alternative because it's going the opposite direction. Well, based on this, am I going to be able to fail to reject and point to that? Well, no, because I'm lower than 0.5. I'm lower than the null instead of higher than the null. And so when your data doesn't support the null, you might as well just stop there because you are going to fail to reject. It will give you, if it doesn't support the alternative, you're definitely going to fail to reject the null. So you might as well just stop and explain, oh, my data does not support my alternative, so I know that I'm going to fail to reject. Okay, so let's run through one example. On shows like American Idol, contestants often wonder if there is an advantage to performing last. To investigate this, a random sample of 600 American Idol fans is selected, and they are shown the audition tapes of 12 never before seen contestants. For each fan, the order of the 12 videos is randomly determined. Thus, if the order of performance doesn't matter, we would expect approximately 1/12 of the fans to prefer the last contestant. In this study, 59 of the 600 fans preferred the last contestant. So does this data provide convincing evidence that there is an advantage to going last? So, state, we want to test at the alpha equals 0.05 level. Okay, if I do not give you an alpha level, just use 0.05. Okay, if I do not give you an alpha level, use 0.05. So my null would be a statement of no difference. P is equal to 1/12, because if there's no difference between the places they are in, then 1/12 should lie for them. And if there is a difference, then P would be greater than 1/12 because we're saying going last has an advantage, which means more people would like it. Okay, and I want to make sure I define P, where P equals the true proportion of people who prefer the last contestant on American Idol. Okay, you notice in the state, I have everything they asked me for. I have my alpha level, I have my hypotheses, and I have defined my parameter. Okay, this right here would give me a perfect score on the state part. Okay, then I say, for plan, we are going to do a one sample z-test for proportions. So I need to check my conditions. One, is it random? And yes, it said that they were randomly selected and the videos were randomly, the order of the videos was randomly assigned. So viewers were randomly selected and order was randomly assigned. Normal. So n times the null would be 600 times 1/12. which is 50, which is greater than or equal to 10. And if I do n times 1 minus the null, that would be 600 times 11/12, which would be 550, which is also greater than or equal to 10. So my normal condition is met. And third is independent. It is reasonable to assume there are more than 6,000 idle fans. Excuse me. Okay, so this is what it should look like, your plan step. State what you're doing, check your conditions. Don't just say random check, normal check, independent check. Actually, write them out and check them. Okay, then the do step. So the first thing we do is calculate our test statistic. So we know that our p hat was 59/600, which would be about 0.098. So then that means z is 0.098 minus the 1/12, which is actually 0.083 if you work that out, divided by the square root of 0.083 times 1 minus 0.083 divided by 600. And if I work all that out, I get about 1.33. Okay, then I find my p-value. Based on that, okay, and going the direction, so I may even come over here and draw a picture. Here's my mean. 1.33 would be here. It wanted more than. So my p-value is, which is the probability that z is going to be greater than 1.33, 0.0918. Okay, we set our alpha value to 0.05. So here is our conclusion. And your conclusion can be exactly like this, pretty much word for word, every time. Because our p-value is greater than our alpha value. And if it was less than, you would say less than. We fail to reject the null hypothesis. Okay, and you obviously, if this was flipped, if p-value was smaller, then you would reject the null. Okay, this is sentence 1. Sentence 2 is where you get your context from. There is not convincing evidence to say that there is an advantage to performing last on American Idol. Okay, so let's break down these last couple things. The do. Here is my test statistic. Here is my p-value. Those are the most two important things with the do. And the fact that you must show your work always. Okay, and then for the conclude, you can literally basically fill in the blanks. Because our p-value is either larger or smaller than alpha, we fail to reject or reject the null hypothesis. There is or there is not convincing evidence to say that, and then all of this right here is just your parameter. Okay? This, cookie cutter this, will get you full credit every time. The first one handles whether or not you reject or fail to reject. The second one handles both the convincing evidence statement and your context. This is gold right here for you. Gold.